Good afternoon to all of you. Today we are going to explore the capability of active imaging microwave remote sensing technique for archaeological study. So here we are going to explore a space-based microwave remote sensing technique as well as the ground-based. So mainly we are going to focus on space-based synthetic aperture radar remote sensing for the archaeological studies. So here we are going to see first the view of spaceborne sensor imageries, and then we will understand what are the advantages, and finally we will try to understand the concept of synthetic aperture radar, which is an active imaging microwave remote sensing technique. And then we will see the capabilities with the help of some case studies which were collected from several research articles, including case studies of IIRS also. And then we will have some concept on ground penetrating radar, which is a ground-based microwave sensor to retrieve information below surface. When we are going to talk about space-based microwave remote sensing technique. So here in this slide, you can see the appearance of a cultural heritage site, that is Angkor Wat of Cambodia. So here I have given the SAR imageries. The SAR is basically synthetic aperture radar sensor. So this synthetic aperture radar sensor is an active imaging microwave remote sensing sensor which is capable to generate high spatial resolution imageries. Now, so here if you will see, so there are four imageries which were acquired by different sensors. First image was acquired by the name is given A. This is acquired by TerraSAR X. The second one is Tandem X. The third one is the C, is the imagery for the same area which was acquired from LOS1 Pulsar 1, and the D is the image for LOS2 Pulsar 2. Now, for visualization in the visible range, I have included here the high resolution optical multispectral imagery of the Google Earth. So here you can see that Google Earth view of the site is visible, and here from the color information we are able to identify, or we are able to do the interpretation in the terms of color, like vegetation could be easily seen in the green color. And similarly, if you will see, this is the main site of Angkor Wat. So here all the walls are clearly visible of the temple. And if we will see in the SAR imagery, so first of all, we should understand the microwave imageries are not sensitive to the color. Okay, so here one can easily see that in these imageries, we are not going to have any color information. Definitely false color composite images could be generated, but the microwave imageries are not sensitive to the color information, so that here you are able to see the bright and dark patches. Like for this water body, if you will see the water which is surrounding the main temple, so this is appearing as very dark feature due to the structural property. Because when we are talking about optical multispectral, so optical multispectral sensors are mainly sensitive to the color information of the top of the surface. But when we are talking about synthetic aperture radar remote sensing, so synthetic aperture radar remote sensing technique, or the microwave sensors, or all the microwave sensors, they are sensitive to the structural property and the electrical property of the object. So here, like scattering will take place according to the structural as well as the electrical property. Now, if you will see, like in this imagery, also we can easily see all the walls of the heritage site. So this could be easily seen. But here, like if you will see in Pulsar 1 and Pulsar 2 images, so here we are not able to clearly see all the walls, but from this appearance, from the appearance of the bright patches, one will be able to identify, or like this is linear feature and walls are there. This is coming due to the resolution, because here the resolution is very, very high, approximately 1 to 2 meter, approximately 1 meter. And here the resolution is approximately 5 meter. And like in the Google Earth imagery view, if you will see, so here resolution is approximately, it will be near to 0.5 meter, approximately 50 centimeters. So here in definitely in this one, we are able to clearly identify the features. Features could be clearly identified in the optical data set. But when we are talking about the structural as well as the electrical properties, so SAR data set will have more sensitivity in comparison to the optical multispectral data set. Now, if you see like this, there is one more water body. So this could also be easily identified here in the synthetic aperture radar imaging. Like all the information, the detailed information of this study is available in this research article. One can go through this. Now, when we are talking about the structural properties, so here we are not going in very much detail of all those, because this will become several images and we will have to mainly focus on the microwave for this archaeological sites. So now this is the another image which is going to which is showing the advantage of SAR over optical data set to retrieve the subsurface. Like here previously we have seen that like of micro data set cannot provide the color information because it is not sensitive to the color, but false color composite information according to the different polarimetric combinations as well as according to the values, variation in the backscatter values, false color information could be provided with the help of the software. So here one can see that this is optical view, optical multispectral view of one of the study area, that is in Sudan. So here one can see that the golden color sand and soil information could be easily seen here. Okay, so we are getting this information in very good manner because all the details could be easily seen. But here a false color composite image is generated with different polarimetric combinations. Like here, what is polarimetry and the polarimetric combination we will learn. But here I am first showing the imageries and then we will go in some details of the theory and then we will understand what is polarization. So here one can easily see that there are these combinations have been used to generate the false color composite imageries. So HS plus VV, HS minus VV, and HB. So these combinations were used. So HS plus VV is represented by blue color. HS minus VV is represented by red color, and HB is represented by green color. So here one can see that with the help of this red, blue, and green color, we are able to generate this false color composite. Now, if you'll see what advantage we are going to see. So if you will see the cursor here, so what we are going to get, like here in the optical remote sensing data set, entire area is appearing as a smooth surface. Here you can see the entire area is appearing as a smooth surface. But the same area, when it was imaged with the help of L-band sensor, approximately 1.25 gigahertz frequency with L-band sensor. So here one can easily see that subsurface information. Here one can easily see that subsurface information, because here the surface is not appearing as smooth. So these paleo channel as well as the paleo soil could be easily detected with the help of the synthetic radar sensors. So here with the help of L-band, so L-band will have the higher penetration capability because this is longer wavelength. So here one can see that this area is also appearing as dry area, because if there will be wetness, it is going to appear as the dark in the optical imagery. So since the area is dry, so the L-band SAR sensor is able to penetrate the top surface of the soil and it is able to interact with the subsurface features. So here subsurface soil, as well as you can see there are several other linear features, and paleo channels could be easily detected in this area. So with the help of synthetic aperture radar dataset, one will be able to identify the subsurface features also. Now, when we are talking about the microwave sensors, so microwave sensors, so they are mainly of two categories: passive microwave as well as active microwave. So a passive microwave sensor detects the naturally emitted microwave energy within its field of view. This emitted energy is related to the temperature and the moisture properties of the emitting object or surface. Passive microwave sensors are typically radiometers. So whenever we are going to talk about the radiometer data set, it means that we are talking about passive microwave sensor. Now there are several applications of the passive microwave remote sensing technique, which includes meteorological application, hydrological, and oceanographic application. The microwave energy recorded by a passive sensor can be emitted by the atmosphere, reflected from the surface, emitted from the surface, or transmitted from the subsurface. So with the help of the radiometer dataset, one will be able to do the information retrieval of different features based on the emitted energy. So passive microwave sensors are also used for different applications, but they have very useful applications in meteorology, hydrology, and as well as oceanography. When we are talking about the active microwave sensors, so first of all, we should understand about active and passive sensors. So passive sensors are those sensors which could not generate their own electromagnetic wave, because here in the case of imaging, to do the imaging or to acquire the data set for any area, there will be a requirement of some kind of electromagnetic wave, some phenomena, like there should be reflected energy or emitted energy or scattered energy. So there will be a requirement of source which could generate the electromagnetic wave. So passive sensors, they could not generate their own electromagnetic wave. So they are dependent on another source of energy. Like in the case of optical multispectral, the data set which you have seen, this optical multispectral data set, or if you'll explore the Google Earth imageries, so these imageries are acquired by optical multispectral sensors, and optical multispectral sensors are an example of passive sensors, and they cannot generate their own energy, and they are dependent on the sun's reflection of sun's illumination from the Earth object. So when the sun's light will be reflected by the Earth surface, so that reflected light will be captured by the sensor, and finally imaging will be done. So that concept we are using in the optical multispectral imaging. Now, similarly, in the case of passive microwave sensor or thermal sensor, generally we are going to use the portion of the emitted energy. So the energy which will be emitted by the Earth object, that will be collected by the sensor to generate the images. So here the passive microwave sensors, they are working on the concept of emission of electromagnetic wave from the object. Now, when we are talking about the active microwave sensors, so active microwave sensors are those sensors which can generate their own energy. They are not dependent on any other illumination. So active microwave sensors, they can generate its own electromagnetic wave, and that electromagnetic wave will incident on the Earth object, and scattering will take place, and the amount which will be returned towards the sensor will be used to do the imaging. And the active microwave sensors are again categorized in two categories: imaging and non-imaging. The most common form of imaging active microwave sensor is radar. Radar is an acronym for radio detection and ranging. Now, in the case of radar sensors will transmit electromagnetic signals towards the target, and it will receive the back scattered energy from the target to generate the images. Now we are coming to the non-imaging microwave sensors. So non-imaging microwave sensors include altimeters and spectrometers. Generally, altimeters and spectrometers are profiling devices which take measurements in one linear dimension as opposed to the two-dimensional representation of imaging sensors. Now, radar altimetry is used on aircraft for altitude determination and an aircraft and satellite for topographic mapping and sea surface height estimation. Spectrometers are also generally non-imaging sensors and are used to make precise quantitative measurements of the amount of energy backscattered from targets. But it is also possible to develop to work with the imaging spectrometer also. But mostly spectrometers are non-imaging sensors. Now this is a microwave band. So here you can see the portion of electromagnetic wave which is covering 1 centimeter to 1 millimeter to 100 centimeter range of the electromagnetic wave is known as the uh, the the microwave band. So microwave band, you can see the wavelength range of 1 millimeter to 100 centimeter is covered. But when we are talking, this wavelength range is mainly used for imaging from space-borne sensors. But like in the case of GPR, like ground penetrating radar, radio frequencies could also be used. Okay, which will have the lower frequency but long wavelength range. Okay, so here one can see that for space-borne synthetic aperture radar sensor, because our main lecture will be, main target will be with synthetic aperture radar imaging. So we are going to focus on the wavelength range which is used in space-borne synthetic aperture radar remote sensing as well as in airborne also. So here there are several categories like K band, X band, C band, S band, L band, and P band. Now what you are going to see when you are moving from K band to P band, K band is covering approximately 0.75 centimeter to 2.4 centimeter wavelength range of the electromagnetic spectrum. X band is covering 2.4 to 3.75. C band is covering 3.75 to 7.5. S band is covering 7.5 to 15 centimeter. L band is covering 15 to 30 centimeter. And P band is covering 30 to 100 centimeter. Now when we are seeing here, when we are moving from K band to P band, there is decrease in frequency. It means that there will be decrease in energy, but there will be increase in the wavelength. Here one can see that frequency is decreasing and the wavelength is increasing. Now due to the longer wavelength, it will be able to, the sensor will be able to penetrate the soil with greater extent. So a longer wavelength ranges are very good for the high penetration. But there will become like one will have to do the like analysis with or the person will have to compromise with a resolution, because when we will have the long wavelength ranges, so we cannot generate very high spatial resolution images. But short wavelength ranges, very high spatial resolution images could be generated. So, but anyhow, our purpose is not to identify the objects at centimeter scale. So the resolution in few meters, like 2 meters, 3 meters, or 4 meters, will be enough for the archaeological applications. Now, when we are talking about the synthetic aperture radar, so synthetic aperture radar is a form of radar that is used to create images of objects such as landscapes. These images can be either 2 or 3 dimensional representation of the object. The remote sensing, which is carried out in the microwave region of electromagnetic spectrum, is known as the microwave remote sensing. And SAR remote sensing is a subcategory of microwave remote sensing. SAR remote sensing is an imaging active microwave remote sensing technique which provides higher spatial resolution images, 2-dimensional as well as the 3-dimensional images. Now, if you will see, so this is a radar geometry. So generally, when we are talking about the radar geometry, so here one can see that there are few directions given, like azimuth direction as well as Z direction. So SAR sensor will move in the flight direction, that is azimuth direction, and it will transmit the electromagnetic pulses in the range direction. All the SAR sensors are side-looking radar sensors, so that they will have the higher capability for the structural properties retrieval. They are not nadi looking, because if they will be nadi looking, they will have the less sensitivity for the structural property, because they will have only the top view of the object. So all the SAR sensors are side looking radar sensors. So here one can see that SAR sensor is transmitting electromagnetic pulses in the range direction. Range direction is the direction in which SAR sensor is transmitting electromagnetic pulses, and one area is covered. So that will be the imaged area, and in the imaged area SAR sensor will transmit the electromagnetic pulses, and here earth object they will scatter. They are not going to directly reflect. Scattering will take place of the transmitted or the incident electromagnetic wave. So after scattering, electromagnetic wave which is incident on the object will scatter in all the possible direction, but it might be possible that some amount of the scattered energy will return towards the sensor, or it will go towards the sensor, so that sensor will be able to generate images based on the energy which is returning towards the sensor. The scattered portion which is returning towards the sensor is known as the back scattered signal or the back scattered phenomena. So the amount of electromagnetic wave energy which is returned towards the sensor after the scattering is known as back scattered energy. There are several other geometric parameters which are given, but we are not going in very much detail. One can go through the classes of introduction to SAR remote sensing, as well as overview of SAR remote sensing and micro remote sensing. Those lectures are available on YouTube. So it might be possible for them to explore all these concepts and all these sensor parameters, because these are required when we are doing the processing. But nowadays softwares are capable enough to read these parameters from the metadata, so that if one is using the already well-known satellite data set, so softwares are capable enough to read these parameters. Now, this is an advantage of SAR versus other Earth observation instruments. So when we are so here comparison is mainly given from LIDAR, optical multispectral, and SAR. So most of the data set which is provided by LIDAR sensors are the airborne data sets. But now ISAT2 and GDI both are the spaceborne sensors. So those data sets are also available, but their resolution is coarser in comparison to optical as well as the SAR. And optical multispectral data set and SAR, both the data sets are available with the help of airborne as well as the spaceborne sensors. When we are talking about the radiation, so since LIDAR and SAR both are an example of active remote sensing techniques, so both will have their own radiation. And optical multispectral data sets are acquired with the help of the reflected sunlight. Now, when we are talking about the spectrum, so LIDAR is generally operated in the infrared region of the electromagnetic spectrum, and optical multispectral is acquired in visible and infrared range of the electromagnetic spectrum. Now, when we are talking about SAR, so this is acquired in the microwave range of the electromagnetic spectrum that we have seen. It is covering approximately 1 millimeter to 100 centimeter. Now here, when we are talking about the frequency, so LIDAR data set should be monochromatic, so single frequency is used. Now, in the case of optical multispectral, so from the name multispectral, it is clear that there will be multiple spectra, and multiple spectra will be obtained from the multiple frequency ranges. So here, in the different frequency ranges of optical multispectral is used, that is covering visible as well as the infrared. And in the case of SAR, one SAR sensor can acquire the data set in single frequency, but when the multiple SAR sensors data set are acquired, so multi-frequency data set could be acquired. Because one will have to keep in mind, like the SAR sensors, when they are operated, so one SAR sensor will acquire the data set in one frequency range only. Like when we are talking about the spaceborne SAR sensors, so spaceborne SAR sensors, they will acquire the data set in single frequency. Okay, because their entire hardware, suppose a sensor is launched in C-band, suppose any sensor is launched in C-band, so that sensor is not going to provide the data set in S-band, L-band, or B-band, or K-band. It is going to provide the data set in C-band only. if I need a data set in X band, so I need to order the data set from any other satellite, which any other SAR satellite which is launched for X band, because the entire hardware configuration will be different for the different frequency ranges. So here for each and every frequency range, there are separate satellites. Like in the case of X band, the very famous satellites are TerraSAR X and Tandem X. For C band, so RISAT-1 was also launched in C band. Envisat SR, JERS, sorry, not JERS, JERS was L band satellite, ERS-1 and 2, and Sentinel-1, Sentinel-1A and B. So these satellites are launched in C band. L band, when we are going to talk about, so LOS-2 Pulsar 2 is currently the L band satellite, which is providing the data set of the Earth's surface in L band. Okay, generally K band we are not using for the space-bound imaging because the wavelength is very, very small. So possibility to get the noise in this data set will become very high. So here one can again see like there are two techniques, polarimetry and interferometry. So due to the longer wavelength ranges, because here one can see that in microwave range, in microwave, the wavelength range is 1 millimeter to 100 centimeter. Now, if you will see in visible range and infrared range, so the wavelength range will be in micrometers. So here one can see that in micrometers, wavelength is very, very small. So they will be there will be large amount or large hindrance due to the atmospheric dust particle. So generally due to the short wavelength ranges, polarimetry and interferometry technique is currently not possible in LIDAR and optical multispectral, because in future it might be possible that if some coherent sources will be generated, and if the exact amount of all these hindrance could be retrieved and they will be removed, so that polarimetry and interferometry may also become in LIDAR and optical multispectral. But currently, when we are doing this practical in laboratory for polarimetry as well as the interferometry phase, so generally in the lab, for the visible range, we are generally using with doing this practical with the sodium lamp. So this is really difficult because in the lab, each and every atmospheric condition parameter, everything is controlled. So, but in the open atmosphere, it will be difficult. But here in the case of SAR, since the long wavelength ranges are used, so they are not affected by the atmospheric dust particle, or even they are not affected by the cloud. So that the polarimetry and interferometry is possible in synthetic aperture radar data, which is not possible in LIDAR and optical multispectral. And there are several applications and models developed based on the polarimetry and interferometry in micro remote sensing technique. Now, when we are talking about the acquisition of the data set, so LIDAR and SAR, synthetic aperture radar, both are active, an example of active micro remote sensing technique. They do not require the sun's illumination or the reflection of the sun's illumination from the object, so that they could be operated. And LIDAR both will have the night vision capability. And when we are going to talk about the weather, so LIDAR and optical multispectral, as we have talked, their wavelength range is in micrometers, so they will be completely blocked by the cloud. And the SAR sensor, due to the longer wavelength ranges, it will be able to penetrate through the cloud. Now, when we are talking about the SAR imaging, so this is an example given of RISAT-1. So here in SAR imaging, what is happening? There are 4 maximum polarimetric combination. Here one can see those combinations. So horizontally polarized electromagnetic wave will be transmitted, and at the time of receiving, horizontally and vertically both the polarization will be received. But since the transmission was there in the horizontal polarization, so maximum energy will be there in the horizontal polarization. But after the scattering, generally polarization is broken, and some amount of energy will also start vibrating in the vertical polarization. So some amount of vertical polarization will also be received. So here one can see if horizontal polarization will be represented by H and vertical polarization will be represented by V. So from single transmission of horizontal polarization, we have the two received polarimetric combination for the polarizations, horizontal and vertical. It means that we will have the two polarizations, HH and HB, two polarimetric combinations, HH and HB, which is generated from single transmission of horizontal polarization. Similarly, when the vertical polarized electromagnetic waves will be transmitted, so it will be so again there will be a receiving of horizontal and vertical polarization. But since the transmission was there in the vertical polarization from the satellite to the object, then the maximum vibration of the electromagnetic wave, maximum portion or maximum energy or maximum intensity will be there in vertical polarization only. But there will be some amount of the energy of the electromagnetic wave which will vibrate in the horizontal polarization also. So from the single transmitted V, there will be a receiving of horizontal as well as the vertical polarization. So here one can see that total 4 polarimetric combinations could be generated, HH and HV, and here from VH and VB. Now this is an animation developed by European Space Agency to show the imaging of synthetic aperture radar sensor. Here one can see that SAR sensor is transmitting electromagnetic pulses. It is able to penetrate the cloud cover and it can provide the information of the Earth object. Here one can see that cities, soil, as well as the water body could be easily detected. Here they are covered by the cloud cover, but cloud cover and haze. But then also SAR waves are capable to provide they are able to penetrate through the cloud cover, and SAR waves are able to provide the information of the Earth surface even in the cloudy situation. So this animation is showing the imaging technique of synthetic aperture radar even in the cloudy situation. Now this is SAR dataset. So here SAR dataset, this is very high spatial resolution SAR dataset which was acquired by IIRS for Visakhapatnam. So here one can see that the different objects, they are identified with the help of the different scattering properties. And here the dataset will have the phase information as well as the amplitude information. With the help of that, one will be able to generate, one will be able to implement the different techniques. And the back scattered signal, because this is generated on this is generated based on the back scattered energy. So back is it means that the scattered energy will have the information of the structural property as well as the electrical property of the object. Now here we are going to talk about the interaction of electromagnetic wave with different soils. So here one can see that in dry soil, there will be less scattering, because what will happen in dry soil, most of the electromagnetic wave will penetrate and only some amount will be scattered, because most of them will be going to the subsurface. So generally dry soil will appear dark in the SAR imagery. And when we will have the wet soil, so in wet soil what will happen, there will be no penetration, because if there will be increase in the moisture content, so due to the increase in the moisture content, there will be decrease in the penetration capability of the microwaves. So microwaves could not penetrate in the wet soil, so there will be scattering from the surface. So scattering from the surface will be very, very high in the wet soil. So here one can see that the wet soil is going to appear as bright object in comparison to the dry soil. Suppose there are two patches of land. In one patch, suppose there is no moisture, and in another patch, suppose there is a high amount of moisture. So the land parcel which is having like very low amount of soil moisture, so that is going to appear as dark in the SAR imagery, and the wet soil is going to appear as bright in the SAR imagery. Now suppose the entire soil is flooded by water. Okay, suppose a layer of water is there. So what will happen at that time? There will be complete surface scattering. You can see here electromagnetic waves are coming from the sensor and they are hitting this target. Since the dielectric constant of water is very, very high, and it will be reflected in another direction, and SAR sensor is here in this direction. So SAR sensor is not going to receive any energy for these kind of objects, because there is no scattering. So these kind of objects like water body is going to appear perfectly or very dark in the SAR imagery. Now these are the techniques which are used by the synthetic aperture radar data set to acquire the information. These techniques are polarimetric SAR, generally these are known as pole SAR. Interferometrics are INSAR, then differential INSAR, D-INSAR, a small baseline subset and persistent scattered INSAR. Polarimetrics are interferometry and SAR tomography. We are going to see case studies which were carried only for a few of them. Okay. So now when we are talking about the polarimetry, so when we are talking about the polarimetric SAR, it means that we are going to talk about all the possible polarimetric combinations. So generally in all the space-bound SAR system, if they are linearly polarized, so there are 4 polarimetric combinations: HH, HV, VH, and VV. HH is representing transmission of horizontally polarized electromagnetic wave and receiving of horizontally polarized electromagnetic wave. So this will become HH. HV is representing transmission of horizontally polarized electromagnetic wave, and after scattering, vertically polarized electromagnetic waves are received. So this will be the combination of HV. Similarly, VH and VB are there. So here there is a definition given for SAR polarimetry. So SAR polarimetry is the science of acquiring, processing, and analyzing the polarization state of an electromagnetic field. SAR polarimetry is concerned with the utilization of polarimetry in SAR application. Now, SAR polarimetry will have the several advantages. Like even here one can see that like there will be 3 to 4 type of scattering which will be given by different kind of structures. Like this structure is smooth surface is going to give the surface scattering. This is structure where like when there will be any vertical structure near to the smooth surface, so that is going to give the 2 bounces. Like first bounce will be here, all the waves will be transmitted, or incident electromagnetic wave will be reflected in this direction. If there is a vertical wall or a stem of the tree, so entire amount will be again reflected to other sensor. So double bounce scatters are going to appear as very bright feature, very bright patch in the SAR imagery. Now when the entire volume of the object is contributing in this scattering, like in the nature when we are going to talk, so vegetation. So first interaction of the electromagnetic wave, when it will incident on the vegetation, first interaction will be there from the vegetation cover. Second interaction will be there from the small twigs and branches, and then big branches. So it means that entire volume of the structure is contributing in the scattering, so that this is known as the volume scattering element. Similarly, there are some other scattering elements like helix scattering. Even due to the special condition when there will be this helical features, formation of helical features, scattering pattern, so that scattering will be known as the helix scattering. But generally, this amount is very weak. Mainly 3 scatterings are playing dominant role: surface, double bounce, and the volume scattering. Now, previously, like in the last slides, we have seen about the SAR polarimetry. Another technique is SAR interferometry. In SAR interferometry, so 2 SAR images are required to do the interferometry. So minimum 2 images are required. So here, if the space-bound SAR sensors are there, so generally one antenna is used to transmit and receive the electromagnetic pulses. So there is requirement of 2 passes. Like in one pass, data will be acquired at one date and time period, and again the satellite will come to the same location by maintaining some distance from the first from the position of the first acquisition, and and from that position again it will do the imaging for the same area with the same SAR geometric configuration by maintaining this spatial distance. This distance is represented by B, which is known as the baseline. So both the images could be used to do the interferometry. So there are several advantages of the interferometry. Interferometrics are uses the differential phase of the 2 SAR images to estimate the surface height. So with the help of that, one will be able to generate the digital elevation model, or if very high resolution SAR images are there. So not only the digital elevation model for the topography, it will also possible to generate the 3D view or the height information retrieval of the object on the terrain also. And SAR interferometry has been widely used for the subsidence mapping and monitoring. Like subsidence mapping could be done at millimeter level. So in archaeological structure mapping, this SAR interferometry technique has been widely used to see any kind of subsidence or to detect any kind of subsidence in the archaeological structure. Now, differential SAR interferometry, when we are talking, so this is advanced version of differential SAR interferometry. So here in differential SAR interferometry, like there is requirement of more than 2 interferograms. So which will be derived either by the 2 data set or 3 data set or 4 data set. And the advanced techniques of differential SAR interferometry are PSINSAR and SBUS. So here there will be requirement of large amount of data sets to minimize any kind of ambiguity or any kind of error in the data set. Because when we are talking about the subsidence in any kind of archaeological structure due to the subsidence in the soil, so that subsidence will be there in the millimeter. So to avoid any kind of this ambiguity or error, large number of data sets are required to do this kind of analysis. Like one study, PSN based study was carried for cultural heritage site of Angkor Wat, Cambodia. So here you can see that Angkor Wat site, Google Earth view, and all the like this is the 3D view created uh, for the temple area. So here one can see that the campus of this area, or the total structure, if you see, this is really very big, and Angkor Wat is the biggest temple or biggest religious place in this world. So here you can see that the single entity of this entire structure could be easily seen, and all the detailed information this is one of the archaeological structure which is studied by several researchers, and not only by the remote sensing, not only by the archaeology, but it has been studied by the people from astronomy and astrophysics also, because the structure of this temple is having very unique information, which is going to talk about the cultural details, which is given in the form of at the like the ancient time astronomy and the cosmology. So there are several papers written. So if you go through the article which is cited here, so all those details, some details you can get in this article also, but those references are also cited, so you can get the information of those details also. Like here, when we did the analysis for the study area, so for most of the location, we found that the temple is stable, because there is no this subsidence was detected, because if you will see 2006 to 2009 data set, so most of the places it is showing to show the green. So here it is showing the zero subsidence, and like from 2014 to 2018, if you will see, so this is also near to zero only, but we are getting some kind of subsidence information. But so that subsidence information, since this is very less, and this requires large amount of data set. So here this is mainly coming due to the variation in the season, because the data sets like we use because limited number of data sets were available, because 10 scenes were available, and most of the scenes were acquired in the season of in rainy season. So in rainy season there will be high amount of variation in the backscattered intensity, so or the backscattered signal. So due to that we are getting some information, but again most of them are close to zero only, because a few studies have shown that some kind of subsidence, but most of the studies they are showing the zero subsidence. In our study also we found that nearly zero subsidence. Now here another study which is carried for Libya, Sabartha, Libya. So here one can see that optical view of the data set is given here for the archaeological site. So optical view of the data set, here you can see that this area, when the same area was acquired by some star sensor. So here one can see that these linear features, these blocks could be easily seen, or you can say that the parcel, because very good linear structure pattern could be easily seen. And this has been verified with the field data set also. So very good information of the archaeological features were extracted with the help of the SAR data set, and the detailed information is available in this research article which was carried by the Chen et al. Now, again, here you can see that different filtering approaches or different techniques were used to enhance the view of the data set. So here one can see that the filter data set. This is the uh, square of the values, SAR data values, which is enhanced with the help of the leaf filter. So here one can easily see that enhancement could be easily seen at different places. Now this is another slide which is going to show the capability of the SAR dataset in subsurface feature detection. Here, if you will see, this is the area of Sahara Desert. So here, golden sand, this could be really detected. Here we are going to focus mainly on the middle strip. When the same strip was imaged with the help of shuttle imaging radar A, in which L-band sensor was used. So with the help of L-band, again one can see that for the same area, which was appearing completely smooth in the optical multispectral data set, is now going to appear as the rough surface which having some kind of structural information in the SAR data set. So here paleo channel information could be easily seen here. So paleo channels were easily detected with the help of the SAR data set in the Sahara Desert. So this information could be detected. Now here we are going to talk about another area. So again, this is the optical image of the area. Now here one can see that these are the microwave images. This is L band and this is the P band SAR. One can see that the high penetration capability is there in the P band SAR, and we are able to get more subsurface information in P band. Okay, this data set was acquired with the help of the airborne SAR sensor. Now again, there are two data sets, one for from the optical multispectral, again from the another from the SAR. So here one can easily see that the SAR data set is showing this paleo channel information due to the subsurface penetration capability. Now this is again another study which is showing the advantage of the multipolarization or the polarimetric SAR for the subsurface feature detection. So here this analysis is given in very good literature for the subsurface structure detection by combining L-band polarimetric SAR and GPR data. So what they found that non-surface scattering regions, including subsurface scattering caused by buried paleosoils, should appear in both HH and HV images. That higher HV by HH ratio and correspond to a lower HH minus VB correlation. So if you will see here, so the image number A is representing the HH polarization of the imagery, and B is representing HV polarization. In HV polarization, there will be if there will be volumetric scattering due to the subsurface penetration, that will be enhanced in the HV polarization. C is representing HV by HH ratio. So in HV by HH ratio, if you will see here, so this feature is enhanced. But if you will see the same feature in the another imagery, so the feature which was enhanced enhanced in the HV by HH ratio, that feature is appearing as dark patch or dark linear feature in HH minus VB correlation. And the object which is appearing dark in the HV by HH ratio is now appearing as very bright patch in the HH minus VB correlation. And E is showing the non-surface scattering map, and F is showing the phase difference between HH and VB signals. So now here one can see that, like we have not gone in the very much detailed analysis of this portion because this trend analysis is already available in this paper. If you are going to use the multiple polarization and multiple polarization and their derived products or polarimetry based derived products, so it might be possible that we will have several unique information which could be detected by taking the different combinations of the polarimetric channels. Like interferometric SAR, we have already seen that with the help of interferometry, one will be able to generate digital elevation model as well as the subsidence. So this is a digital elevation model which is generated for one area Fujiyama mountain. So I have taken just to show the digital elevation model 3D view of the Fujiyama mountain. I have not taken for any other archaeological site, but one can do for the archaeological sites also. Like again, this is the 3D structural view of the Toon Valley. So Shivalik range and the higher Himalaya range could be easily seen here according to their elevation values. Now another study, SAR interferometry based, another study was carried by another researcher for a location in China near to Beijing. There is one location, one study site, that is Summer Palace. So the Summer Palace, this study was carried by Tang et al. So here in this study, when they use the PSM SAR technique as well as they use the small baseline interferogram also to generate the deformation map. So in this study, they found that the subsidence as well as the upliftment both were recorded. So here you can see that the range is in between -6 to -6 to -3 centimeter, which is represented by red color. Similarly, there are different color representation. So most of the location is showing the displacement greater than -1, but these needs to be carefully studied because these locations are mainly covered by the vegetation area. So generally, long wavelength ranges like L band and like airborne P band data set, if it is available, they are going to give more fruitful result. So very good study was carried and very good analysis was done, and you can get the literature information from here. Now another study was carried in the Vietnam. So here high resolution TerraSAR-X small baseline in SAR images were used. Like here, this is not used for the subsurface penetration. This site is in urban area. So land subsidence was monitored, and velocity map of Hanoi Historical Center was measured, and its values is represented here. So line of sight range could be easily seen here. The line of sight range is from -15.6 centimeter to +4.5. And vertical displacement is -21 centimeter to not centimeter, -21 millimeter to +6 millimeter. Okay, but for most of the location, what we are going to get, this green color we are getting, but for these locations, for the locations which are represented in red color, we are going to get the maximum subsidence or displacement. Okay. So similarly, another study was carried. In this study, the damage extraction was done with the help of the high resolution SAR data set. So one can easily see that this study was carried for the Kathmandu Valley. So here you can see that the changes were detected, and here one can see that subsidence near to -1 millimeter per year was detected here. So one can easily find this information. The same area which is represented here in blue color, dark blue color, now here shown in the high resolution world view 3 imagery, and the detailed information is again given here in this image. In this literature. Now we are going to talk something about the ground penetrating radar. Quickly we will go to the ground penetrating radar, and we will see one case study, because there were several case studies, but I am going to show the result of only one. So ground penetrating radar is a tool archaeologists are using more and more for in the 21st century. GPR allows archaeologists to survey archaeological sites in a short amount of time with precision and without digging it. But each and every technology will have its limitation. The main thing that the soil should be dry, but even like if there will be some vegetation information like the grasses are there, so using the long wavelength ranges of ground penetrating radar, one can overcome this problem, and it can provide the information of the buried object or the subsurface information. Now the basic principle of all the active microwave sensors are similar. They uses microwave energy. So here, in case of ground penetrating radar, so no need. Generally, people are preferring to do the analysis with long wavelength ranges. So radio waves are used to create picture of underground before excavation. A picture is used to locate any variation in the subsurface. Electromagnetic waves emitted into the ground and time measured for wave to be reflected and received. When wave hits areas of change in soil, it is hit back to receiver antenna. Now, based on that, the changes in the soil will be detected. Okay, change in soil can include the object buried underneath the surface. When we are talking about antenna, so like here, there is like I took it from the literature. So higher frequency, so greater vertical resolution. Vertical resolution will be greater in higher frequency. And lower frequency, it will have lower frequency means wavelength will be very high. So it will have the greater penetration depth. So here one can see that 100 megahertz. So one will have the penetration up to 4 to 25 meter. 300 megahertz 1 to 10 meter. 400 megahertz 0.5 to 4 meter. 500 megahertz 0.5 to 3.5 meter. 900 megahertz 0 to 1 meter. So it depends on the soil condition also, because if the soil will be completely dry, and so it might be possible that penetration may be more even with the small frequency GPR. Now, when we're talking about the vertical resolution, so vertical resolution formula is given here. So it is depending on the frequency of the antenna and relative dielectric permittivity, that is represented by RDP. So here, if you see the formula, so vertical resolution, which is the minimum thickness which could be detected by the GPR, is given. So that is represented by Tm. It is equals to C, that is the speed of the electromagnetic wave or light in vacuum. That will be divided by 4f multiplied by square root of epsilon. That is the relative dielectric permittivity. So relative dielectric permittivity, that could be obtained for any kind of surface, because this is the ratio of the dielectric permittivity of the substance divided by the dielectric permittivity of the vacuum. So this could be easily calculated, and the vertical resolution then could be calculated. Okay, so here one example is given. If 4 megahertz antenna is there, relative dielectric permittivity 10, the minimum thickness is about 6 centimeter, which could be detected. Okay, so here one can see that the vertical resolution is mainly depending on because C will be generally fixed. So this is mainly depending on the frequency as well as the RDP. Now, a relative dielectric permittivity, when we are talking about RDP, is ability of a material to store and allow passage of electromagnetic energy when a field is imposed upon it. RDP of substance, so how to calculate it? So electrical permittivity of substance divided by the electrical permittivity of vacuum. So here one can do, this could be easily calculated. Now here one can see that image is generated at a good horizontal resolution at different depths. So here you can see that when the depth is increasing, So information, subsurface information is also increasing. So here one can see that when the GPR was operated, so it will be possible to generate 2D view, and it is also possible to generate the 2D view in the vertical direction. So one will have the reliable information or the information according to your choice with the help of the GPR. One limitation of GPR is it should be operated manually for the area, and it might be possible that that will be time consuming, as well as it is going to take high amount of cost also. Okay, so like generally people are doing the first observation if the area is dry and the wavelength, long wavelength data sets are available like L band and P band. So they are preferring to do either airborne survey or spaceborne survey, spaceborne star survey, so that large area could be covered. Because before using GPR, one should have some information of the study area, or not some information, detailed information, so that the subsurface information could be detected. And thank you for attending this lecture. And we will start our question answer session after 5 minute break. Thank you.